Every year, factories around the world produce more than 12 billion bullets. To achieve this staggering number, enormous amounts of lead, brass, and chemical compounds are required to manufacture such a lethal device. But how are bullets made? To find out, let's travel to the United States, the world's largest producer and consumer of ammunition, and visit one of its factories. The history of bullets is as old as gunpowder itself. In the 13th and 14th centuries, when this explosive mixture arrived in Europe from Asia, armies began experimenting with rudimentary projectiles. These were hand-cast spheres of stone or lead, fired from primitive cannons and muskets. Although revolutionary at the time, these weapons were slow and inaccurate. It wasn't until the 19th century, with the invention of the unified metallic cartridge, that bullets took a technological leap forward. This design combined the projectile, the propellant, and the primer into a single unit, allowing for faster reloads and more accurate shots. Throughout the 20th century, innovations such as conical projectiles, copper coatings, and more recently, advanced polymers refined their design. These improvements allowed bullets to adapt to a wide range of uses, from personal defense to high-precision sport shooting. A modern bullet is a sophisticated system made up of 4 essential components, each engineered for a specific purpose. The casing, usually made of brass or steel, serves as the structural housing that holds all the other elements. The primer, a tiny detonator, produces the initial spark when struck by the firing pin. The propellant, an advanced chemical compound that replaced traditional gunpowder, creates a controlled explosion that propels the projectile forward. And finally, the projectile itself, the tip that cuts through the air at speeds that can exceed 1,500 meters per second. It's typically made of a lead core wrapped in a copper or nickel jacket to optimize its flight and resistance. Each part, made from materials like nitrocellulose or stable explosive compounds, is designed to withstand the extreme pressure and heat generated during a shot. But how are these elements combined in a modern industrial production line? Before manufacturing begins, the raw materials go through strict quality control. The brass is analysed with spectrometers to detect any impurities that might weaken its structure. The lead is inspected to ensure uniform density, which is crucial for projectile stability. The propellants, highly volatile compounds, are tested in specialised labs to verify their chemical composition and explosive behaviour. These materials are stored in climate-controlled chambers equipped with sensors that monitor temperature, humidity, and pressure to prevent any accidents. Only once they meet these rigorous standards are they approved for the production line. The process starts with the manufacture of the casing, which serves as the structural base of the bullet. It begins with massive rolls of brass or steel that are unrolled and cut into flat discs using high-precision laser cutters. These discs, about 2 centimeters in diameter, are the starting point. Next, hydraulic presses capable of exerting up to 300 tons of force mold each disc into an initial cylindrical shape. This process, known as deep drawing, requires millimetric precision, as any defect in the casing could lead to catastrophic failure when fired. Additional presses then refine the shape, elongating the walls and forming a cavity at the base for the primer. Once formed, the casings go through a laser marking system that prints essential data such as the caliber, batch number, and manufacturer ID. This marking not only helps with traceability in the supply chain, but also plays a crucial role in forensic investigations, allowing a bullet to be traced back to its origin. Afterward, the casings are submerged in chemical baths that remove lubricant residues and metal particles. They are then dried with compressed air jets and pass through automated inspections using high-resolution cameras that detect imperfections invisible to the human eye. In a large-scale factory, up to 12,000 casings can be produced per minute, each one identical to the last with astonishing precision. The next step is one of the most delicate, the loading of the propellant, the component that gives the bullet its explosive power. Black powder, an unstable mix of charcoal, sulfur, and saltpeter, is a thing of the past. Today's modern propellants, based on nitrocellulose with stabilizing additives, offer more controlled and efficient combustion. These compounds arrive at the factory in sealed containers, transported under strict safety regulations. They are stored in underground bunkers equipped with advanced ventilation systems, smoke detectors, and trained personnel who monitor conditions 24 hours a day. A single spark could trigger a catastrophe, which is why handling the propellant is done with almost military precision. On the production line, high-precision dosing machines measure the propellant with a tolerance of less than 1 milligram, depositing it into each casing through calibrated nozzles. Optical and weight sensors ensure that the amount is exact, while a vibrating platform distributes the powder evenly, eliminating air pockets that could alter pressure during firing. Operators, wearing anti-static suits to prevent accidental sparks, supervise the process from control booths while high-speed cameras monitor each stage. This balance between speed and safety makes the process resemble a pharmaceutical laboratory more than an industrial factory. Next comes the installation of the primer, the small component that initiates the chain reaction. This piece, about the size of a grain of rice, contains highly sensitive chemical compounds such as leadazide, which produce an instant spark when struck by the gun's firing pin. Due to its explosive nature, primers are manufactured in a separate facility, where precision robots mix the compounds and encapsulate them in tiny metal discs. These discs are transported in sealed containers to the main factory, where automated machines insert them into the base of the casings. A hydraulic press ensures perfect alignment, and optical sensors verify their position with micrometer accuracy. Each casing then undergoes a pressure test that simulates the impact of the firing pin, ensuring the primer will function reliably. The projectile, the visible and functional part of the bullet, is next in line. Its design must balance weight, aerodynamic shape, and impact capacity, adapting to specific uses such as tactical defense or precision sport shooting. Manufacturing begins with lead ingots melted in furnaces at over 300 degrees Celsius, becoming a dense liquid poured into molds to form cylindrical cores. These cores are rapidly cooled to preserve their shape, then molded in high-power presses to achieve their specific geometry according to the caliber, from 9mm pistol rounds to 7.62mm rifle projectiles. To improve performance, the cores are coated with a thin layer of copper or nickel through electroplating, a process that reduces barrel friction and increases projectile durability. Final inspections with lasers and microscopes ensure that each projectile is free of cracks or deformities. In the assembly stage, synchronized conveyor belts align the projectiles with the loaded casings. Automated presses join them with precise force, creating a tight seal that guarantees the integrity of the cartridge. High-speed cameras verify that the projectile is perfectly centered, since even a slight misalignment could alter the bullet's trajectory. But bullets have not always been made of lead. During World War I, lead shortages led some factories to experiment with steel projectiles, or even wood coated in metal for training purposes. It was a creative solution that kept supply lines running during a time of crisis. No bullet leaves the factory without undergoing a thorough inspection process. Machines equipped with ultrasonic sensors, lasers, and high-sensitivity scales analyze each cartridge, checking its weight, dimensions, amount of propellant, and projectile alignment. High-resolution cameras detect microscopic defects such as cracks or imperfect seals. Inside an internal firing range, random samples from each batch are fired under controlled conditions. Engineers use chronographs to measure muzzle velocity and ballistic sensors to analyze trajectory and impact. Everything is evaluated: shot consistency, accuracy at different distances, and casing integrity after detonation. If a single bullet fails, the entire batch is pulled for complete review because a defect could be dangerous for the shooter and those nearby. Approved bullets are cleaned one last time to remove any residue and are then sent to the packaging area. Automated machines sort them by caliber, type, and purpose, placing them into sealed boxes designed to protect them from moisture, dust, and impact. Each box includes labels with detailed information: batch number, manufacturing date, projectile type, and safety warnings. In a factory of this scale, up to 8,000 cartridges can be packed per minute, enough to fill a truck in under an hour. Pallets of boxes are then moved to logistics centres, from where they are distributed to destinations as varied as military bases, police academies, sporting goods stores, or shooting clubs. ammunition transport is subject to strict international regulations. Each shipment is tracked through digital systems with security cameras, armed escorts, and protocols that ensure the bullets reach only authorized hands. This level of control reflects the responsibility inherent in producing an object with such potential. The manufacturing of a bullet is a testament to human ingenuity, where simple materials like lead, brass, and chemical compounds are transformed into tools of precise engineering. Yet, this process also raises profound questions. A bullet can protect lives, shine in competitive sports, or cause irreversible harm, and its use demands judgment, training, and respect. Today, the industry is embracing innovations that go beyond traditional materials. Advanced polymers, used in training rounds or specialized applications, are gaining ground due to their lightweight properties and reduced environmental impact. These developments not only enhance performance, but also point toward a more sustainable future for ammunition manufacturing, reducing reliance on heavy metals and minimizing waste. If you enjoyed today's video, leave a like and subscribe to the channel. Let me know in the comments what you thought of this process and which one you'd like to explore next. In the windows below, you'll find more videos you're going to love. See you next time.